You are screen sharing. Okay. Oh, sorry, yes. I am going to record our presentation today. Caleb's away for the entire class at a meet and track meet. So I'll get this up onto YouTube and then I'll put the link on our page in case you want to refer back to the presentation. I'll go ahead. And then I guess one other difference is I have an anonymous survey for y'all to fill out later. Maybe we'll take a we'll cover some content, and then when we need a little break, I'll hand this out. So I just like some feedback about the course. You are, of course, encouraged to do the the official online feedback. Have those emails started yet? Not quite yet. Soon, I think I got one already saying, hey, we're about to bother all the students. So you'll start getting those. And yeah, I'd appreciate if everyone, could do the responses and the comments. And I read all those. My boss does too. And I'm not saying don't put anything critical. I'm just saying that we do take those very seriously. So, any feedback you have, and that is, completely anonymous. So feel free to say anything you want there. There's a couple of ideas that I kind of wanted to ask about, and maybe I'll tell you the 5 questions now so you can, they can marinate a little as we talk about some content. The first 3 are more straightforward. 4 and 5 are kind of open-ended. So we had 5 modules this semester. How many modules do you think would be ideal? So 4, 20, what would you like? And obviously you won't be retaking this class. Hopefully no one is retaking this class. But this class has benefited, or y'all have benefited from comments from previous students. So hopefully, you can pay it forward for future generations. Based on your ideal number of modules, so let's say you say 10 is perfect, how many of those do you want to be a paper evaluation? How many do you want to be presentation? So this year it was 2 presentations, 3 papers, but last year we actually did 5 presentations. So I think it's 5. What skills would be beneficial to develop in our course? So I said examples, reading, research, data analysis. So these are some ones we did, but you can suggest things we didn't do, of course. And the last one is a surprise skill, so look out for that. And 4, which aspects of our course would benefit the most from improvements or a complete rethinking? And I almost said, like, what was the most frustrating? So, I mean, if you're like, this really doesn't work, then, just let me know. And the last one is more about, okay, what can we do about that? So do you have any suggestions on how to improve our course? So I'll hand these out later. You don't need to put your name on it. And I guess we can just do like an anonymous pile at the back. And you don't have to complete anything, but if you want to leave any feedback in this way, that would be great. And of course, there's the soon to be online official course evaluation as well. All aboard still? All aboard. So I should be recording. All right. So those are the 2, I guess, different things for today. This is our, the start of our last module. I left an extra week and off to get sick, but so far class hasn't been disrupted by that. So we have 2 weeks of office hours if you want help with your final assignment. And then it will be due. We can't have things due right at the end of the semester. It's not allowed. So we're encouraged to say the scheduled exam date is when your final paper is due. So we don't have a final exam per se. It's just the final paper is due on Friday, May 5th. But if you want to do it earlier, that's fine as well. We'll come back to, well, I guess the rest of today we'll be talking about kind of the content for the final paper. But let's look at the class data from the flanker task, which I think worked out pretty well. This was a new task. We didn't do this last semester. I say last semester, but it was 2 years ago when I taught this previously. The last time I taught it, we did the Simon task. We'll see it briefly today, but it doesn't work out very well on an individual level. And the flanker task is much nicer because although the results were somewhat different, I think everyone kind of saw that incongruent was longer than congruent, and neutral. And that's the typical results in the literature. You know, sometimes neutral is a little slower than congruent, sometimes congruent is a little slower than neutral. I'm curious if they have a meta-analysis on this yet to say, hey, is that just normal sampling variability, or is one easier than the other? But you typically see these pretty similar, and then incongruent, you know, much longer because of that conflict between the arrows facing the different directions. We'll revisit this data today. So here, this analysis is, you know, reaction time means, and these are the standard deviations. That's 2 standard deviations. And we're going to look at doing a distribution analysis. And one of the examples we'll look at is doing it on these data because we're already, you know, familiar with them. Questions about the flanker experiment? Here. So reaction time distribution analysis, kind of the core content for today. So why are we talking about this? Well, we'll get to the scientific rationale, but the practical rationale is that's what we're going to do for our last assignment. So we're going to go to the lab, we're going to do a little experiment, and this one isn't based on historical literature, so I'm not actually sure what's going to happen, which is kind of fun. And then to analyze our data, instead of just doing reaction time mean and standard deviation, we're actually going to look at an ex-Gaussian distribution. We're going to fit that to our data and use that to interpret our results. That's the practical reason, but let's go through scientifically why that's important. Okay, here we go. Okay. So most things in life, most data that we collect has a normal distribution. And you can think of this as probabilities. So let's imagine height, for example. If we went around and we, you know, let's say just adults, so because, you know, children obviously would be shorter than adults. But once people are fully grown, if we go around, measure people's heights, most people are of average height. So the most likely, you know, before you measure someone, before you find them, we would predict the most likely height that they would be is the average height. And then the chance that they're very, very tall, there are some people who are very, very tall, but the probability decreases. You're less likely to run into a very tall person. Same with, you know, very short people. You're less likely to randomly sample someone who ends up being, you know, 4 feet tall. So that's our normal distribution, and most data fit a normal distribution. A lot of physiological human data, you know, height, weight, you know, grip force, you know, all sorts of things we measure are normally distributed. And when we have a normal distribution, what we need to describe these data are a measure of central tendency, and typically we use the mean. But in this case, the mean, the median, the mode are actually identical. So that would tell us kind of where the peak is. And then to measure the distribution, or how much variation there is, we need a measurement of variability. So we could measure variance or standard deviation. And just variance is the square of the standard deviation. So if we know the mean and the standard deviation, we essentially know what the distribution looks like in the population. There we go. Thank you, PowerPoint. Now, the challenge with reaction time and other data, another great example is salary, is it is not normally distributed. It has a skewed distribution. And the skew here, because the data is more to the right, we call that a positive skew. If it were to the left, that would be a negative skew. And when you have a skew, the mean, the median, the mode are no longer identical, and the mean, which, you know, we like to use for a few reasons with reaction time, and gets pulled in this direction. So you can imagine you've got a few data with really high reaction times, and that pulls your mean towards the right. Now, to describe a skewed distribution, we would need, say, the mean, the standard deviation, but we also have to measure, well, how skewed is it? And we do that with skewness, or sometimes just referred to as skew. So we have been, you know, talking about reaction time with these two variables when we should have really been using all three, because we know it does have a skewed distribution. The challenge with skewness is that to measure this, you really need hundreds or thousands of trials. And rarely And that would be for each participant. And we, we don't want you to come in, well, it'd be nice if you came into the lab for 1,000 trials, but that would be a very boring experiment, right? So sometimes we could, measure skewness accurately, but typically we can't because we don't have hundreds or thousands of trials for each participant. So here's an example data set. This is from the Simon task. This is my data from 2 years ago. The Simon task, you might have read about it when we were talking about compatibility, because Stroop, Simon, they're kind of all in that realm. But for Simon, I won't go over the exact task, but it's very similar to being compatible, two choice, and then contralateral, so ipsilateral versus contralateral. There's easy trials, those are the compatible ones, and there's hard trials, those are the incompatible ones. And what I did is I actually tested myself on what the students did, but I did it 4 times so I could get 256 trials in the compatible condition. And this is a histogram of my reaction time. And it very nicely shows a skewed distribution. So if we cut out these, that would be probably a symmetrical normal distribution, but there's not. We see a few trials with long reaction times skewing the distribution to the right. So here, I said, hey, MATLAB, what is the mean? What's the standard deviation? What's the skewness? It will tell me these values, but if I did a few hundred more trials, these should be similar, but this could change drastically. So it's difficult to rely on skewness for measuring the skew of a distribution. And this is where there's an alternative technique. Also, the way we're going to talk about this is this part of the distribution, the part that looks normal, we can say that these are the majority of trials because, most of the trials fall into this normal distribution. The part that are in the tail to the right, we're going to refer to those as the minority of trials. It's still far more common for my reaction time to be in this range than it is to be in this range. This happens, but not very often. Okay, so just to summarize that so far, we can reliably measure reaction time mean and standard deviation, which we've been doing, but we cannot reliably measure reaction time skewness. And we need that if we really want to describe this skewed distribution. So the alternative, which the paper introduced, is to fit an X-Gaussian distribution function to the reaction time data, and we can describe this. It's going to have its own parameters. We're not going to use mean, standard deviation, and skewness, but we're going to have 3 new parameters, mu, sigma, and tau, that are similar. But thankfully, we can reliably describe those data. We don't need thousands of trials. So we'll say, okay, here's the data. MATLAB magic fit an X-Gaussian distribution function to it, and then tell us the parameters of that function, the mu, sigma, and tau. So those 3 parameters, mu, and we'll look at this pictorially, is the mean of the Gaussian distribution. So Gaussian is just another word for the normal distribution. I think this is named after the mathematician Gauss. Does anyone know that off the top of their heads? I think so. I think he was, yeah, you want to look up there? Pretty sure he made many contributions, but I think he was kind of famous for, studying the normal distribution, which was posthumously named in his honor, I would suspect, Gaussian. So we can think of the mean of the Gaussian distribution, that is the mu parameter. We can think of the standard deviation of the Gaussian or normal distribution.
It's named after Carl Friedrich Gauss.
That's okay.
Who first developed a 2-parameter exponential function in 1809 in connection with studies of astronomical observation.
Wow, okay. What country was he from?
Germany.
Germany. Okay. There we go. That's Gauss. Thank you. That's some good knowledge you got there in the back of your head.
Yeah. Went back in the day.
So 2 of the parameters describe the normal or Gaussian distribution. Tau, that parameter actually explains how skewed it is. And we'll look at pictures of it. So what is an X-Gaussian distribution function? Well, the short name comes from exponentially modified Gaussian distribution, and it's really just saying that the X-Gaussian distribution function is the literal combination, I think the right mathematical term is convolution, of a normal distribution or Gaussian and an exponential distribution. So we take these two, put them together, and that gives us an X-Gaussian distribution. So fancy name, but it's really just two distributions combined. Here we have a normal distribution. And instead of asking for the mean and standard deviation, here I've put down the mu and the sigma, which is essentially the mean and the standard deviation of this. They're synonymous at this point. Here is an exponential distribution. And I don't know why, but I don't know if it was just whoever taught me math, but when I think of exponential, I think of kind of rising. Does everyone else think of it rising? Or you think of it falling? I don't know. To go back to high school, maybe. But I did check with Wikipedia, and exponential are typically described as exponentially decreasing. I guess you can also think of something exponentially increasing. Two sides of the same point. So here's our normal or Gaussian distribution. This is an exponential distribution. We can describe the mean and standard deviation of this with a single parameter, tau. And here it happens to be 110 milliseconds. So if we convolute these, or I'm not sure if that's an appropriate term, but if we add these together, that is what convolution is. So at every time point, we're going to add these data points together. We get this function, the exponentially modified Gaussian distribution function. And you can see that this kind of looks like reaction time, right? Like it's not completely symmetric. There's a skew to the right. And those three parameters combine from those two different distributions to form this combined distribution. Now, where did I get this example from? Well, that was actually from MATLAB when I said, hey, here's 256 of my trials, compatible trials on the Simon task, or just think about, ipsilateral on two choice. So, I've got this skew, and I said, hey, MATLAB, fit an X-Gaussian distribution function to it. And I said, okay, this is what fits your data. And the way we describe the X-Gaussian distribution function are with those three parameters. So it wasn't pulled out of the hat. I used that example because that's the best fit to my reaction time data. And I kind of like this slide right here because I've superimposed them. And that you can see here, yes, this distribution function does have a nice fit to the histogram data. And the probability density and the frequency, those are kind of two ways to measure the same thing. Okay, any questions about that so far? Does this seem wildly unusual, or it's just not too bad? It's okay. It's a bit different, I suppose. A bit mathematical. The good news is we're going to be applying this to reaction time. We're not going to be proving the mathematical functions or anything like that. Okay. So with your data for the new experiment, what I'm going to challenge you to do is not interpret the means and standard deviations, but to interpret there's two conditions, and each one will have an X-Gaussian distribution function. And then you're going to have to say, are they the same? Are they different? How are they different? So we're going to practice that kind of in three steps. First, we'll just look at changing one parameter at a time. Just kind of, the simplest way to look at a change. Then we'll look at two real data sets where, more than one thing might change at a time. So I took my actual data. I think that's the same as what we saw. Let's check. Again. Okay, so the black curve, that is my actual data from when I did the Simon experiment. And red, what I've done is I've made a change to one of the parameters. We're going to do one parameter at a time so we can see how it affects the shape of the distribution. In this example, I increased mu by 20%. And I did 20% so that we'd have a nice, visible difference. If I only increase this by 1%, the two lines would probably be just on top of each other. You could do decrease, but in this case, I just decided we would increase one parameter at a time. So when I increase mu, So remember, mu is the standard, is the mean of the normal distribution part of these combined distributions. So in black, mu is 308, and in red, mu is 307. And what that has an effect of is it just shifts the data to the right. And if I had decreased mu by 20%, then the black curve would have shifted to the left. So when mu changes, the distribution shifts either left or right. Not too crazy, just a shift. What happens if we change sigma? So sigma, remember, well, from the normal distribution, that is the standard deviation. So if there's a small standard deviation, it's a tight normal distribution, a big standard deviation, there's more variability. The way we see this is kind of in two ways, and the more important of the two is probably shown right here. If we increase the standard deviation of the normal component, we're going to see the left tail, check directions there, the left tail gets pulled to the left. So sigma for the black curve is, about 30. When I make it 30.6, what's going to happen is this curve is going to get pulled to the left. Now, we're not going to see it so much on the right because the curvature of the right is controlled more by tau than it is by sigma. So when we're looking for the effect of sigma, we want to look just at the left side. We'll look at the right later when we get to tau. Now, the other thing you probably notice, maybe the more obvious change, is that the peak is lower. Now, why has that happened? Well, this is a probability curve. So the area under the curve has to be 1 or 100%. And you can't have more than 100% probability. So under the curve, we have to have 100% probability. So if I'm gonna, in the green, if I'm gonna pull this way, and now the probability is here is larger, the probability elsewhere has to decrease. And we see that most visibly at the peak. So when sigma, for example, gets larger, we pull the tail to the left. And because there's now more probability here, we need less probability somewhere else. And that's visible most obviously in the peak of the distribution. Tau, we're going to see something similar, but instead of on the left, it's going to be on the right. Because remember, tau is what describes the skewness of the distribution. And here, tau, I increased by 20%, just like the other parameters. And what we can see, and it's maybe easier to see than it was for sigma, is that the tail, the blue curve, is being pulled to the right. So tau is larger, we have to have a more skewed distribution. It gets pulled to the right. And because we've added all this probability here, and under the curve has to be 100% probability, the peak is going to get lower so that we still have 100% under the curve. If we had decreased tau, then we would have, the right tail would have been pulled to the left and the peak would have actually gotten higher. We would see the opposite. So any questions about manipulating one parameter at a time? Let's do two real examples. That was made up data. The first one is going to be the Simon task. And it's actually just my data. And then we're going to do the flanker task. And for the flanker task, I used all of our data to look at the change between conditions. All right, Simon task first. So we saw the compatible distribution already. These were incompatible trials. And when we plot them like this, they kind of look the same. But if we look at the parameters, mu is larger, sigma is larger, and tau is actually smaller for incompatible trials. And a better way to plot these, and how I'll ask you to do it on your assignments, is to plot them on one graph. Because here it's like, oh, they kind of look the same, but once you plot them on top of each other, you can see some visible differences. Okay, so let's walk through what's happened. And we have, all three have changed. So it's more complicated than those previous examples. But the good news is we can just go through one at a time and try to understand what's happening. And this is exactly what you'll do on your assignments. Okay, mu. In black, it was 308. In red, it's 375. So it's gotten larger. So what we expect from that is that the whole distribution for the red will shift to the right.
Right.
So for mu, we expect a rightward shift, and yep, we can see that. That's kind of maybe the easiest one to know. So great, we understand the first change. Second change, sigma is larger. So for this red distribution, remember we should look to the left tail, it's going to be pulled to the left. It's hard to see here though, because this one's already to the right, so these lines aren't on top of each other. So one way you can do this, to understand this leftward shift, is I drew a line at the same spot, so at this level of 1, from the black curve to the peak. So I did this in PowerPoint, so I knew exactly where the peak was. And I'm going to do the same thing for the red at about the same spot. We don't want to do it here versus here. It's got to be at the same level. And we want it to be fairly low so that we're capturing the tail. So I drew it from the side of the red to the peak. And what we should see is that this is bigger than that. That's what happens when sigma gets larger. Now it's a little hard to see, so then what I did is I aligned those two lines. And you can see, yes, definitely the left tail, although it's maybe not obvious visually, when we measure it, yes, the sigma, this left tail is larger for the red than the black, and that's because sigma is larger for the red than the black. Let's do that again, but now with tau. Ooh, the other thing, remember when we said, when we pull something to the left, the peak has to get lower. We don't see a lower peak here, and that's because when we look at tau, we're going to see the peak should get larger, and peak getting smaller, peak getting larger. In this case, they look to have almost like perfectly canceled each other out. Okay, tau. So tau, unlike our theoretical example, tau actually got smaller. So if we take the red curve, or we take the black curve, what we need to do is not pull it to the right, but pull it to the left. So the amount of skew should be smaller for red than it is black. Maybe not visually obvious, so I did those lines again. So here's from the peak over to the tail of the black, and then from the peak of red over to the tail of red. And what we're expecting is the red one to be smaller. And if I align them, yep, you can see that, yes, the red one is definitely smaller than the black one. And when the tail gets pushed in, because we've gotten rid of area under the curve, the peak's going to have to get higher. So we still have 100%. So the peak in this case should be higher. Why haven't we seen it change? Well, that's because larger sigma should decrease the peak, smaller tau should increase the peak, and it looks like those have canceled each other out nicely, and the peaks look quite similar between the two conditions. I don't know if this is exactly what will happen with your data, but this is an example of a real change in probability distributions. So a little summary of, I guess I could have color coded this a little better, but so mu, the change in mu shifted the data to the right, larger sigma shifted the left tail to the left, and a smaller tau shifted the right tail also to the left. Did anyone read about the Simon task? I feel like it was in a few of the SRC papers. Does anyone remember it? It's one of those ones that kind of lives in the same realm of, Flanker, Simon, Stroop. Ooh, okay. So how would we write about this in the paper? If these were our data, how would we describe it? So this is what I would imagine in the results section, and we'll come back to this when we get into your assignment. So the mean of the normal distribution, just a reminder, it went from 308 to 375, or that was our mu parameter. So I would say the reaction time of the majority of trials, so when we're talking about mu and sigma, that's the majority of trials, tau is the minority, that's the tail. The reaction time of majority of trials was longer in the incompatible condition than the compatible condition. So that is a decent way to explain the change in mu for these data. What about tau? Oh, sorry, sigma first. So this is about the standard deviation of the normal or Gaussian distribution, again, the majority of the data. So the reaction time of the majority of trials was more variable in the incompatible condition than the compatible condition. And finally, we have tau, which describes the tail. Sometimes this is also called the rate parameter. So for the minority of trials, so when it's tau, it's the minority of trials, with long reaction time was shorter and less variable in the incompatible condition compared to the compatible condition. And tau, remember, it measures both the mean and the standard deviation of the tail. So that's why I included, it's shorter, that's referring to the mean, and less variable, that's referring to the standard deviation. All right, one more example. Let's look at the flanker task. And now it's all of our data together, kind of give us the most accurate prediction of the results in the population. And this is what we found. So neutral and congruent are very, very similar. So the green and red are kind of right on top of each other. The mu parameters, very similar. Sigma, maybe a touch smaller. Tau, maybe a touch smaller here. I don't think I actually ran stats on this, but for today, I just said, these are comparable. So we'll just talk about neutral, congruent, kind of as one condition, and then incongruent, definitely visibly different, right? And in your assignment, if you're so we'll only have two curves in our assignment, and if they're on top of each other like this, yes, you can also probably assume that they are comparable. So we'll just go with like a real visual analysis. Whereas blue, blue looks different than green and red. So on the next slide here, all I did is average together, neutral, congruent. I left the two curves on here, but I just averaged their parameters. So this will be more like your assignment where we're comparing one condition to another condition. All right, so what do we see? And I tried to color code this here. So mu for the neutral congruent is 362, and incongruent is larger. So remember, that should shift the distribution to the right. So we can see, yep, the blue distribution is shifted to the right. I kind of will look at the peaks to see, where they are in space. Yeah, that, shifted. I think we have an arrow. There we go. Yep, and it's shifted to the right. What about sigma? Okay, sigma is larger for the incongruent. So if we go to the left tail, that should pull it to the left. It's hard to see which one is larger because they, one descends here and one descends here because they've been shifted. But we can do that line trick again. So here's from the green line to the middle of the peak, and here's from the blue line to the middle of the peak. And then when we align them, sure enough, we can see, yes, sigma is larger for the incongruent condition. Ooh, now, because it's larger, the peak should get lower. And yes, we can definitely see in this case that it is lower. And that's because tau is going to also have the same change on the peak. But remember, tau is referring to the right tail. So the larger tau for the incongruent should pull the right tail to the right. And we can do our little measurements to kind of check that. And sure enough, yep, tau is larger for the blue curve, as visually and numerically. And because tau is larger for the blue, that is also going to decrease the peak. And so now, instead of them canceling out, like in the last example, they're both pulling it down. And that's why we got this really big decrease in the height of the peak for the incongruent distribution. Any questions about that example? This is how I would describe it. So, for the results, you should have a figure. This is explicitly stated on slides later. There should be a table with the parameter values, and then this sort of text would be appropriate in this case. The reaction time of the majority of trials was longer in the incongruent condition than the neutral condition. So that's what's happening to mu. For sigma, the reaction time of the majority of trials was more variable in the incongruent condition than the neutral and congruent conditions. And then tau, for the minority of trials with long reaction time was longer and more variable in the incongruent condition compared to the neutral and congruent conditions. So we're going to look at all three parameters. You can look at them numerically to think about what's happening, and visually I think also helps. You should, as long as these are large enough changes, you should see some sort of visible change in your distribution. It is possible that, they'll counteract each other in, say, the peak. But generally, each is somewhat independent because, the mu is where is the peak, sigma is where is the left tail, and tau is, where is the right tail. Take a peek here. Do we want to do the survey now? Yes, Brandon has decided. So let's do the anonymous survey now. I suppose you can do it later. So yeah, just those 5 questions, and you can write something or nothing. You don't need to put your name on it. And I guess when we're done, if you want to pass them all back to Jake, maybe if you want to make a pile back there.
Brandon, I really think Sparkle Pina is too hard. Sparkle Pina? Yeah. But Sparkle Pina is already there. No.
Then
Did
you
you already?
said the meetings moved around, so they moved up there. Younger me.
Sorry to spring this on you, if you have more deep thoughts later, feel free. You got the official course feedback. You can also always come chat with me or email me too. Or email my boss. Maybe I'll pause the video or to resume recording here. Jake, are you okay if we continue on? Okay. All right, so let's talk about the experiment we'll be running. So we'll talk about that, and we'll talk about kind of expectations for the last assignment. So some important content here. So we are going to run a true experiment in that I'm not sure what the results are going to be. We are going to compare reaction time to press a switch, which is kind of what we've been doing in other blocks. It'll be 2 choice, so stimulus, press, stimulus, press, to releasing a switch. So imagine now that you're holding the buttons down, and if you get a right stimulus, then you should release the right button. So it's key press or key press, one or the other, versus key release. So a small change. And the question is, does that change reaction time? Now, I don't know. I'm not sure what to expect here. Is there a study out there that has done this exact manipulation? Maybe, probably. I haven't found. There was one I was looking at yesterday, but it was kind of weird, the things it was doing. So I'm not really sure kind of what is out there in terms of being like, yes, it's definitely this way or the other way. So a real true experiment. But I thought maybe we could brainstorm for a moment, or maybe just your speculation on whether it'll be faster to press or to release. And so one thing, when you release, you have to fight against gravity instead of going with gravity. So let's see, I don't know, did I get that right? When you press, you're with gravity, so that would make pressing faster because gravity is working with you, for example. Any other thoughts? So these could be, mechanical, related to the keyboard. They could be biomechanical, related to the body. Could be neurophysiological, related to the signals, or they could be even cognitive psychology related to information processing. Any wild ideas? So you start with a poll. So I feel like pressing is going to be faster. That says who agrees with that? And then how many people think releasing? One releasing, and then undecided. We got 2.
Oh wait, are we voting?
Yeah, just casually. What do you think?
I think release moves.
Presumably slower. That seems to be the popular opinion, but I'm not really sure. Any other thoughts on what might be easier for one than the other? Another one I thought of is to release. You know, you're contracting, and you have to like stop that contraction and go in the opposite direction. So is that more complicated because there's like two things to do? Whereas to press, you're fairly relaxed, and then all you have to do is increase that motor activity. So maybe
Are you contracting though to press down a keyboard key? Are you contracting? You haven't contract to press it, but once it's there, you kind of just
to hold it
kind of
down.
just weightless.
Yeah, maybe it's gravity just. Oh, when I did it, I felt my forearms getting sore, so I felt. And I was like, oh, I gotta put the keyboard somewhere else. So feel free to adjust the keyboard so it's comfortable when you're holding it down. Maybe I'm just getting old and weak. But let's see, releasing, well, see, maybe a benefit for pressing is it maybe less complicated. Well, no, I'm gonna say less complex is probably a better terminology. So it's like the muscles just have, so I guess you contract the flexors. Whereas for release, a negative is that you have to inhibit flexors and contract extensors. Yeah, I don't know.
But for pressing, aren't you having to inhibit your extensors?
Well, yeah, there would be. I mean, they're not initially active, but yeah, typically our motor drive, when we say, do this, the drive is, excite here, and also, make sure not to turn this on. So yeah, this is a bit different. It's maybe more, it's not as cognitive psychology drenched or versed in theory as the other modules. So one thing for your papers, I do expect them to be, a little more hypothesis driven and exploratory, and hey, this is what happened, and oh, okay, maybe this is why. And if you happen to find something great in the literature that 100% supports what you find, that's awesome. But we also might not be able to find that someone who's done exactly this thing before and explained it in all of its facets. So there's going to be 4 blocks. 2 of those are pressing and 2 of those are releasing. It will always be an ipsilateral mapping. It'll be counterbalanced whether you do, so you'll do two pressing and 2 releasing, or 2 releasing and 2 pressing. So that will be counterbalanced. You won't switch between them multiple times, which is another way we could do the order. Each block has 16 practice trials followed by 58 trials, test trials. And if you remember the reading, to measure the X-Gaussian distribution function in an individual participant and condition, we want 100 trials. So you're going to do 2 blocks, so we should get 116, which is more than the minimum amount with a little bit of breathing room there. And half the time you'll be pressing left or releasing left, and half of them will be right. For the apparatus, it's the same computer, but I've swapped in a mechanical keyboard so that we know more about how the exact switch works. And what I tried to do is go with switches that hopefully pressing it and releasing it from the keyboard standpoint is fair or comparable. Because with the other keyboard, it was a membrane switch, and I don't know how much force it is to press versus release. We'll look at the keyboard in a second. We don't know all the details, but we at least know more of the details, and it's hopefully a fair press versus release from the standpoint of the keyboard. But in your paper, you might argue, if you want, that it's not, that there's something different about it. So this is the keyboard. It is actually in the lab as well. And so it has brown key switches, TTC. I was trying to get the cherry brown, but couldn't find it for an affordable price. So we got the knockoff cherry MX switches for those of you familiar with gaming keyboards. But brown switches, they have a tactile feel to them, so when it actuates, you'll feel it has like a click to it. And the specs are as follows on the next slide, it kind of explains these. So it takes 44 centinewtons to get a force to get the key to actuate. So a centinewton, which would be 100th of a newton, or is it thousandths? 100th, yes, centi, right, okay, metric, I should know this, I'm Canadian. How far does the switch travel until it actuates? And actuate means that the computer registers it from going from, not pressed to pressed. So, well, I guess we can use a keyboard here. So on these keys, for example, I can press it a little and it hasn't actually actuated. The computer hasn't said, oh, you've pressed L yet. I have to press it so far with so much force until the computer says, oh, you pressed the button. So that's called the pre-travel. It travels 2 millimeters until it gets to that actuation point. And that takes 44 centinewtons to get there. Now keyboard, these are a little different. Oh, sorry, I have other buttons in my lab that are a bit different, but keyboard keys typically, after they actuate, so I push it here, it actuates at this point, you can keep pushing it. And that's called over travel. And this keyboard in particular, it has 1.8 millimeters of over travel. So you push it 2, it'll say, oh, you pressed it, and you can actually keep pushing it 1.8 millimeters. The total travel is literally the combination of the pre-travel and the over travel. So that's how we get to 3.8. Another schematic of that here. So imagine this is the button and you start to push it down. And this is where it actuates. This is where, the switch makes contact inside of it. And the computer says, oh, you pressed the button. So this is the pre-travel. It's a little hard to read, but hopefully in your slides it looks better. So that's pre-travel for us, it's 2 millimeters. So it says, oh yeah, you've pressed it. You keep pressing it, and it'll still say, yeah, you've still pressed it, but there's over travel to keyboard keys or switches. So it will go another 1.8 millimeters. Now, if you've pushed it all the way and you start to release, it has to travel up, and you would think, okay, it's going to say you stop pressing it at the same point as you pressed it. They actually don't work that way because of their mechanics. And it will actually stop being pressed a little bit higher than where it detected the original press. Now this, sometimes they call it hysteresis, and typically in keyboard land, they call it differential travel. I don't know what it is exactly for these keys, but we know that this is 1.8, and it's going to be a little higher, and let's just maybe assume that it's 0.2 millimeters. And the nice thing about that, if it is, that would make this 2 millimeters, and it would also make that 2 millimeters. So in other words, to press the key, it has to travel 2 millimeters, and to release the key, it has to travel 2 millimeters. So that's why I went with this keyboard. So hopefully it's traveling the same distance for a press and for a release, so that it's a fair comparison. Because let's say to press, you had to press 2 millimeters, but to release it was 10 millimeters, then that should have a different reaction time, or probably would have a different reaction time. So here, they're probably both 2 millimeters. The amount of force to go from here to here was 44 centinewtons. They don't say exactly what it is from here to here. So that's another kind of question mark.
Who's got a force platform for the keyboard?
You can,
Yeah.
there is a device you can buy. I think it's very expensive that will test your button. I should see if I can find a video of it and send it out. But it's literally like a little plunger, and it pushes the button, and it can change the force, and it knows where it is, and it also will gather the signal of when the button says I'm pressed, I'm released, and it will spit out like those metrics and like dozens of others that just fully describe your button. And I think it's so expensive that on the website it says like you can rent it.
Where did somebody even discover that that's something they want to know?
Yeah, I don't know, but I'm sure there's lots of human factors research on keyboards.
In the world.
Yeah, so pro gamers, very interested in this. Pro gamers don't typically use brown switches, which have a tactile feel. They typically use red switches, which are linear. And I wish I had brought those now. I have some in the lab. They typically travel the same up and down, they acquire the same force, but there's no click in the middle, like as there's no tactile feel. And the reason gamers like those, they're not great for typing because it's hard to tell, did I press the key? Like you don't get that proprioceptive sense, but they can go up and down really quickly. So if you're, I don't know, shooting or whatever one does in a video game, you can do that really quickly. And there are some brands that have said, okay, typically 2 millimeters down, 2 millimeters up is kind of standard. Well, I said, well, let's make that 1.5 and 1.5 so you can be even faster. And I'm a bit curious. I should find more about the research behind this. So here's pressing, two choice, very much like what we've seen before, although I did invert the colors on the screen. So now it's a black screen with white stimuli, which is hopefully a little easier to look at. And then releasing, would look something like this. The trial actually won't start. So in pressing, the trials, kind of just keep coming. Releasing, the nice thing is, if you take your fingers off the button, it will wait for you to go back to start the trial. But try to do the 2 blocks in the same way so that the results are comparable. Don't do all the pressing trials and then release, be like, I'm gonna take a 5-minute break and another 5-minute break, because that's, adding confound. For MATLAB, it's very similar to before. There's a program, reaction time distribution analysis, and you put in your participant number, the block number. So it's 1, 2, 3, or 4. 1 and 2 are pressing. I just split it in 2, so you've got a little break. So it's, you don't have to do 150 trials at once. You get a little break between. And then 3 and 4 are releasing. So there's a sheet that shows your counterbalance. You'll either do 1, 2, 3, 4, or 3, 4, 1, 2. Once you do that, I am almost done the second program, build Excel file. You put in your participant number, you run that, and on screen, it will spit out your parameters. So it'll tell you mu, sigma, and tau for pressing and releasing. And it will make an Excel file that has your probability distribution in it. And we'll look at that next to see how you work with that data, but it's actually, I think it's simpler than how we've processed data before. It kind of actually spits out kind of the final data because to get the X-Gaussian distribution, I couldn't ask you to do that in Excel. That's something MATLAB has to do. Excel might be able to do it, but might also be complicated. So this is the example, an example of the data that it will spit out. So you'll need to import it into Excel the normal way. If you try to open it, it'll be weird. So you gotta go data, import. There's 3 columns. I've labeled them here. The first is the reaction time. So that's your X-axis. And then this is for pressing and releasing. And these numbers are probabilities. So at 13 milliseconds, so think about going along the X curve, what is the probability of that being your reaction time? And these are, very, very small values. So it's essentially 0. And that's because, this is my data that I tried analyzing here. I didn't have any trials with 10 milliseconds of reaction time. In these data, the bad trials have already been excluded. So practice has been taken out from this, and too fast, too slow, wrong target. So let me open these data here. Okay, example data and figure. Here we go. So the X data is going to go from 0 to 1,000 milliseconds, and I'm kind of assuming everyone's reaction time distribution will fit within that. But if you have really slow reaction time, let me know, and I can always fit the X-Gaussian distribution out further. These are my probabilities for pressing. This is for releasing. And what we want to do essentially is make a figure where we have both X-Gaussian distributions on one graph, so they're easy to compare. And that's actually really easy to do. We highlight our 3 columns, and we don't want a line plot, we want a scatter plot. And Excel is smart enough to know that, hey, I'm going to use this X-axis for these data and for these data. At least it was last time I tried. Let's see what happens. Okay, there we go. Let's just make this a little bigger so we can see it. And if you want, you can add, lines between these points, or you can get rid of the dots and make it just lines. Style is up to you. Just make sure it's easy to see. So let's see, I think, yeah, oh, down here it's starting to tell me. So blue, well, it's hard to see, but blue is my pressing and red is releasing. So there's, things are happening, but I'm not sure if this is the same. 3 people have tried this so far, myself and 2 students in the lab. And I think 2 of us showed one benefit for one condition, the other person showed a benefit for the other condition. So not sure if 2 of us are crazy or 1 of us are crazy, or if different people will have different results. And then from there, it's a matter of kind of cleaning up your figure and making it look nice and pretty. So the original data, remember I said it'll plot your distribution from 0 to 1,000, but I'm guessing your distribution will fit within that. So one thing to make this prettier is I just said, okay, well, I forget where I cut it, but I don't need to show this data, that's just 0. So we could maybe go to 100, 150, and then it looks like by the time we get to 500 or 600, it's just zeros. So in this plot, I said, hey, just focus on where we see actual values above 0 in these distributions. Any questions on, in the lab, the data and that sort of stuff? And if you have any issues, let me know. I'm around. Okay, last and maybe most importantly are expectations for your papers. So it's it's a research paper. I decided not to up it to 3,000 words. I'm sure I don't think I'll have any arguments. If you want to write 3,000 words, you can. One reason I didn't is because in the other papers, there's lots of articles that you could find and maybe add them in and talk about. Here, I don't think that's the case. And I'm going to challenge you to find something that can explain your data, but it's not like you've got 1,000 articles to choose from as you would have with Simon, or sorry, not Simon, stimulus response compatibility, Flanker. There's so much stuff on that. Here you're going to have to get a little more creative with how can I explain this in terms of well, we'll get to that in a moment. So 2,000 words, if you want to do longer, that is fine, but it shouldn't be much shorter. Individual partner, like before, due date, APA format. It should start with the title page, end with the references, and we'll talk about the sections in the middle briefly. So introduction, we've seen this before, and I'll actually cycle back to some tips in a moment. Method, we've also seen some people use these sections, some people didn't, and both can work. But if on your last paper I complained about your method, maybe try using the explicit sections, that might help. And for your procedures, when you're talking about doing the task, definitely include a figure. It's just far easier to understand than a paragraph. Although I know what you did, but a paragraph of text is being like, then there was a fixation, then there was a box, just picture. much easier. Results. So what I would like is a figure of your 2 X Gaussian distributions on one axis, so they're easy to compare. This is just the flanker example. I guess I could have gone with my actual data on this experiment. I would like one table, and if there's more things you'd like, that's fine, but this is the requirements. This table should have your 2 conditions and your 3 parameters, mu, sigma, and tau. Nothing too crazy. And then also some text to support your results. And you can use this as a template for how to write about mu, sigma, and tau. You might not get an increase or might be a decrease, but that same sort of logic is fine. So not a ton of text required in the results section. Discussion, we've seen this before, but maybe some more poignant comments or based on kind of changes. So here, we've had a hypothesis in the past, but it's kind of just been like, hey, we expect the normal thing. Here, I'd like you to come up with a hypothesis. And there's no wrong hypothesis. You could say, I think this one's gonna be faster, I think this one's gonna be faster, I can think they're gonna be the same. And, it'd be good to say why you think that, going in. You don't need to explain distribution analysis. So think of your past paper, you didn't explain means and standard deviations, you just assume the reader knew those. And in this paper, you don't have to explain, mu, sigma, and tau. You're gonna have to describe how mu, sigma, and tau change. But all the stuff I talked about today where I said, oh yeah, normal distribution doesn't work for skewed distributions, you don't need to worry about justifying using ex-Gaussian distribution functions. Discussion, so even in the APA table we saw earlier, they suggest beginning with support or non-support of your hypothesis. So that should be explicitly in there. It doesn't have to be right away, but you make a hypothesis, discussion, return to your hypothesis. And then this is where you might have to get a bit creative with your interpretation. And these are some ideas, and you could touch on, one or more of these. Your interpretation, you should be talking about what you saw in your distribution analysis. I guess that's fairly we'll say that's mandatory. You might want to pull in some cognitive psychology theory. So let's say one is faster than the other. Could that be because of response selection is different, response programming is different? And then maybe some neurophysiology. And that could be, like gravity, is it less complex? Any of this, your knowledge about the motor system. I guess the neuromuscular system. So including, biomechanical aspects as well. Okay, very last part. So anything on anything so far? Very last thing, and this is kind of group feedback from what I saw across, multiple assignments. I would love to see some better titles. A lot of titles were just like stimulus response compatibility. I'm like, oh, that's more like the assignment title. Maybe come up with something more interesting for your title. This is a weird one, but the introduction section doesn't actually begin with introduction. It begins with your title, which is odd, but it's an APA format thing. And here I brought the rest of that. Oh, no, sorry. I do have the full copy of that paper that you were reading, and you'll notice here if we go, this is the introduction, and see it doesn't actually say introduction, it repeats the title. So weird but true. And let's see here. APA figure and table formatting, some people were fine, some people hadn't quite nailed this. So those websites are great resources, but we can look quickly here at, I think I have at least a couple of figures. I skipped the first one because okay, here's a giant table, but it starts with the table number, and that's bold. Then there's a title. I actually should not have that. Ooh. It's italicized, and it's in title case. And then, so there's even, there should be horizontal lines, but no vertical lines. So take a look at the formatting for tables, and then figures. Oh, wow. So I did not have that right. But so it has the figure number in bold, and then the title of the figure italicized, and then in the title case. And optionally, you can include a note at the bottom, and there is a format for that. Note is italicized, and then the rest is not. Okay. You should reference your figures in the text. And APA actually says that before the figure appears, there should be a reference to it. So if you're like, oh, do I put the figure here or here? Make sure you say, hey, see figure 1. And then anywhere after that should be, figure 1. Same for tables. Reaction time, just a reminder that we should talk about it as being shorter or longer, not faster or slower. And 3 significant digits is fine. So if your mu is 336.63, you could just have that as 337. For smaller values like tau and sigma, you can still go with 3 significant digits. So 49.0, not 49.04. I don't know if that was so much in the paper, but definitely in the presentations, I saw some tables where it was like point blah 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 blah, because MATLAB, of course, spits out all the digits. Abbreviations, I actually suggest not using abbreviations because they make it harder to read. The exception is for very common ones. I think reaction time, if you want to use RT for reaction time, that's okay. And the format for it is the first time you say reaction time, you should say reaction time in brackets, RT, and then from then on, always use RT. There's a small exception in figure captions, but I won't worry about that. You can look into it if you want, but I won't penalize you for that one. For period is one word. Word does not like it, but it is one word. Method, your method section is that should be singular and actually not plural. That's maybe more of a personal pet peeve. Not sure exactly APA's standpoint on that. Well, I don't think I have that here. Page breaks. So if you need, your references should be on its own page. And what you don't want to do is just go, enter, 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 enter. Because what happens if you change anything that might not be in the right spot, it might be too high or too low. And as I go in and change things, all of a sudden it jumps around. So I'm sure a lot of you already know this, but you can use a page break. So okay, well, that's one example. So see how my references are on another page, and I don't just have a bunch of enters here. What I did is I said, okay, we want to insert page break, and boom, jumps to the next page. What else we got? I think references. The most common one, and I think this is probably from, often I go to Google Scholar and grab the reference and plug it in. Google Scholar, although it says APA, it doesn't do this perfectly. So the name of the journal should be in title case and italicized. The journal volume should be italicized, but not the comma and then not the issue number. So let me show that. And sometimes you'll have a volume number and no issue number. Okay. So this was under review, so that's not a great example, but here we go. So behavior research methods, note it's italicized, it's title case, this is tiny. It's italicized, it's title case, and then this is italicized as well, but the comma is not, and neither are these brackets or the issue number. So that's the volume and the issue. So when you copy and paste from Google Scholar, you probably have to go in and then, do the italics and even the title case sometimes. Okay, but those were some things that I thought would help, more than one person. Thank you, everyone. I'll be here next week, the week after. I'll also be online, email. Let me know how I can help with your assignments.